Alexei Semikhatov from Lebedev. He's going to either speak to us, depending on where you looked at slides, on screenings in conformal field theory and beyond, or screenings, etc.
Thank you very much. I want to thank the organizers for the invitation and for this opportunity to speak in this beautiful environment. And I must tell from the very beginning, I do share the responsibility with the previous speaker, the responsibility for tonight's event. So I will also try to finish 5 minutes earlier, certainly not a single minute past the time. I will speak.
Thank you. Send the microphone on.
Of course, I forgot the mic, right? One always does, right? Must be working now, all right? Thank you. I will speak from the standpoint of grassroots, of where categorical things and equivalences in particular are being forged, produced, so to say. And this is conformal field theory, which has known to have contributed a lot to a number of concepts which are now has taken off since then and are now being discussed in the context far or already quite remote from the original ones. But now has come when conformal field theory takes back some of it has also been developing, and is now taking back what people are doing in other areas, and that's why the subject might be, this conference is interesting for me, and the subject might be of some interest to some of you. So what people, simple-minded people like me, are so-called physicists, are interested in are, let's speak about two-dimensional conformal field theory models and models of statistical mechanics, which include a number of interesting and funny things like the very famous sand pile model and the two-dimensional percolation model. These turn out to be, some of these, and the two mentioned ones, turn out to be logarithmic conformal field theory models. I will comment on my next slide what logarithmic is. Logarithmic is synonymous to non-semi-simple. So what people need to know in these theories, they need to know correlation functions, which say that in the percolation model, if I observe a percolation cluster here, what's the probability that and how many percolation clusters are going to be observed some distance from my observation point. For the correlation functions in technical terms are correlation functions of fields. So people need to know what fields are and technically what primary fields are. And primary fields are highest weight states, as a matter of fact. They put in quotation mark because they can be some generalized highest weight states, but never mind these morally and in many cases literally highest weight states. So people need to know representations of algebras and conformal field theory models. And then for the reasons that have been emphasized a number of times, you have to know categories, but that's difficult. The algebras you are dealing with, even the simplest one, Verazora, are infinite dimensional, and the complexity grows very fast. So the standard practice, of course, is to discuss another subject. Once a problem is unsolvable, turn to another one, and then maybe you will at some point you will come back to the original problem. So what I will discuss today is not so much the subject that I have just described for you, but a reflection of that subject in the mirror. And the mirror has a name. It's called Kazhdan-Luste correspondence, and what it roughly does, it replaces the field theory infinite dimensional setting of conformal field theory with very often finite dimensional setting of Hopf algebras. So the reflection in the mirror is somehow contracting, but quite often delivers quite a lot of information, and we will see how this happens. So, as I said, on the other side, through the mirror, you encounter Hopf algebras or quantum groups, often finite dimensional. The strategy of problem solving with a mirror is not new. Perseus used it to solve problem that was facing him, and he was, as we know, quite successful. even if destructive. The original idea of Kazan and Lustig was that a category equivalent to a suitable O category from a finely algebra can be at the same time can be a subquotient of representation category of a quantum group at root of unity. There is a very particular root of unity appears. The idea then, that was already several decades ago, they already then propagated to logarithmic conformal field theories, which turned out to be very special because they are naturally defined, logarithmic conformal field theories are naturally defined as kernels of screening operators, and the idea of screening operators is what is underlying the Kazan-Lustig duality. For the first 20 years of conformal field theory, people were mostly doing what they called Russian conformal field theory models, semi-simple in the first place, and there the tool that has been used broadly was Feld-Debye complexes, and the homology of those complexes produced for you the space of states, those primary fields you are looking for, and sometimes could even allow you to at least start computing your correlation functions. In logarithmic conformal field models, in logarithmic theory, you no longer take the homology, so things become actually simpler in a way. You just take the kernels. You don't have to quotient over the image of more or less the same tool of Feld-Debye complexes. A remark which I have promised: why logarithmic means non-semi-simple. I have a Jordan cell here in the first two lines. I think it's upside down, right? The one in front of H is downstairs rather than upstairs. So this is the matrix read off from the right-hand side is a Jordan cell with eigenvalue H and 1 in front of f of x, which is unfortunately below the diagonal. So if you solve these differential equations, the system of differential equations, you do get logarithm in the second line over here, and that's exactly how logarithms appear in correlation functions as soon as you have Jordan cells for your Virasoro generators. So as soon as Virasoro generators and the left-hand sides up here are part of the Virasoro generator, acts non-semi-simply, you are doomed to have logarithms in correlation functions, and because non-semi-simple is a mouthful, it's much easier to say logarithmic, and it's sexier somehow. So people usually speak of logarithmic conformal field theories, just the same as non-semi-simple. So the idea of the mirror is the idea of a dual pair, and I will be discussing this in various versions of this for the rest of my talk. So you take a vertex operator algebra or conformal field theory, and you realize that your fields, that the algebra that defines that theory for you has a centralizer, something commutes with it, and whatever commutes with it is called, that's not a rigorous definition, but whatever commutes with your algebra is called screening operators or screenings. The name is historical, and I'm not sure about why they're screening. Well, at least not to explain it now. So how this works? Usually one starts with a suitable lattice and then takes a lattice vertex operator algebra, and the lattice VOA can be viewed as a Hopf algebra freely generated by exponentials, which, now that we're talking about Hopf algebra, group-like, and primitive elements, which are currents and their derivatives. The useful thing that we will need later on is a Hopf pairing. So with values in fractional powers, Laurent series with Laurent polynomials with fractional powers, and the denominator here is of course read from the scalar products that you have over here. I never asked if there is a chance to use a pointer or anything. This thing does not allow me to do this, or it doesn't have a pointer in it.
There is an enormously long stick in the corner.
There is a long stick. Ah, very good. Thank you. Thanks very much. So makes things much easier then. So right. So this is of course the fractionality is determined by the scalar product that you have here. This depending on your lights. I'm not specifying anything at this moment yet. So that will I also use later on. So I pause on the very formal notation here. So I also have again the structure of yet a Greenfield lambda module on my Lights VOA. So what it does, coaction just takes care of the exponent of this exponential. So just it's kind of grading, which comes out here. That's a technical point, and I'll write it as people usually do with coaction in Hopf algebra notation. And the action, I think, will not be used much. So the VOA structure follows by the VOA map. There is a variable z starts floating around here. It's omitted from notation over here, but you always understand where you have several such variables, then you can indicate which one is where. This is just a variation of the standard, nothing more than standard stuff about VOAs. You also need to have the Razor element, and the Razor element is constructed by taking a dual basis over here and taking this quadratic combination with the linear term here, and then the q's are a parameter, can be used as a parameter, and the central charge of the Virasoro that you get is just rank minus 12 q times q. So as to have at least one formula entirely and 100% comprehensible in my talk, I just quote the Virasoro algebra here. So that's where C appears in the Virasoro algebra. Now, screenings are these guys. You take action, you define how screening acts on any element of your algebra. You take a particular exponential and you take the residue, and an important piece of the condition that screening is something which commutes with your symmetry algebra. So far I have only Virasoro. So for the screening to commute with the Virasoro, this has to have Virasoro dimension 1. And I write residue, and I will comment later on what this residue actually means. So sometimes I prefer thinking of it in physical terms as an integral, and the integral contour is an old story that you can draw it in various ways. So the definition is a little bit ambiguous, but the details are ambiguous. But later on I will make it specify exactly what I mean by the residue here. Now, as I said, it annihilates this operator annihilates the Virasoro, or if you wish, depending on your standpoint, commutes with the Virasoro generators, if you somehow view this as kind of a joint action, if and only if you have a quadratic equation for this. The exponent sitting here has to satisfy this quadratic equation given the q that defines your central charge. It has two solutions, and the two operators corresponding to the two solutions are called long and short screenings. One is long, the other is short. It's a little bit conventional, but in particular settings, short screening are by convention doing one kind of things, and long screening are doing other kind of things. The famous example of a theory extending Virasoro algebra and doing this logarithmically is the triplet or Gaberdeel-Cauchy model. This is a model based on the Virasoro on a W algebra W of P for every P greater positive integer P greater than 2, and it extends the Virasoro algebra. And the story, as we now know, develops on two sides. in terms of logarithmic conformal field theory and in terms of the quantum group. So here we have the W algebra, which will appear on the next slide, and the quantum group, which mirrors it through that magic mirror on quantum group side, is a version of quantum SL2 at particular root of unity. So there is this 2 should not be here. I'm sorry about that. 2 should not be here, otherwise everything is fine. Yes. So it's a finite dimensional quantum group because you factor out over central elements, e to the p and f to the p. K to the p is central, but it's not equal to unity. K to the 2p is equal to unity. And this is a finite dimensional Hopf algebra. Not quasi-triangular, as a matter of fact. And on the other hand, we have this notation means that we have an infinite dimensional algebra generated first of all by Virasoro, by the energy momentum tensor, which conventionally has dimension 2, and by 3, hence triplet, fields of dimension 2p minus 1. Once again, p is a positive integer greater than 2, greater than 1, which you fix from the very beginning, and it also sits at this root of unity, which has to be corrected, however, by removing that too. I will skip the nomenclature of Hopf modules and everything, and just tell you that basically you deal with a free field construction, and you define your algebra, just those fields. You find them by studying the kernel of a particular map among in the Felder-like complex. I'll skip the details. I will just tell you the summary of what was going on here. The triplet algebra is generated by energy momentum tensor. And the Virasoro primary fields, 3 Virasoro primary fields, which is a triplet under one of my screenings. So they are in the kernel of the short screening. All the fields are in the kernel of the short screening, and the 3 fields are just mapped, as you see from their definition. You take this exponential, then you apply the long screening once, then apply the long screening once again, and you span out the triplet, and these turn out to have just the conformal dimension 2p minus 1. And this is the most studied example of logarithmic conformal field theory. And it has been compared in many details with what's going on the quantum group side. So the quantum group that I just had on my previous slide with due correction has exactly 2p simple modules, and the triplet algebra has 2p simple modules. And my quantum group, its representation theory is not that terribly difficult. So you figure out what the projective modules are, and as much as is known about projective modules here, and now a lot more is known, confirms that they have the same structure, the same Levy diagram. Then you can ask yourself, what is the Grothendieck ring of your quantum group, and you compute it, and you realize that this is C of x over this particular combination of Chebyshev polynomials, and here is the ring that you get. And as much as was computed mostly by brute force in conformal field theory, just by direct calculation with computer, as much as computer could go, supports this, and every consistency checks and indirect arguments also supports that here we have just the same, so hence the check mark over here. from Grothendieck ring, we can actually compute the full-fledged tensor products, not decomposing indecomposables on the right-hand side. So projective modules occur on the right-hand side, and a lot less is known on the field theory side. But everything that is known also confirms that this is the same. Indecomposables were indeed, some of the indecomposables were calculated by a certain NAM, Gabbard-Diel-Kaush computer algorithm. This quantum group has 3p-1 dimensional center, and the triplet algebra, somehow there's some conspiracy such that exactly same finite dimension comes out is in the form of the space of torus amplitudes. So these not only the characters of your irreducibles, but there is a bigger space, and it turns out to be exactly same dimension. And now a simple adaptation of Lubashenko's theory defines for you SL2Z action on your center, and you compute this action, and you realize that there's particular representations, whatever this notation here is, and then you do the same with the characters and with the space of torus amplitudes in field theory. So you do totally different calculations upstairs and downstairs, and you arrive at the same representation of SL2Z. There are just as many simple modules and that big center. So in a way, every simple module by Drinfeld map, of course, has an image in the center, but there are more things to generate this whole center, and these produced by modified traces taken over projective modules. And conjecturally, I'm not sure this has been brought to a computation, but these are supposed to be done in field theory side by Miyamoto's type pseudo traces, which should produce remaining torus amplitude. And finally, a nice thing is that the Riemann element in here is exactly e to the 2I pi, 2 is correct here, 2I pi L naught. So there is the two worlds are in touch, at least here. Actually, quantum group and conformal field theory share common center, and this language allows you to directly identify them. I will skip this discussion and rather ask this question: how perfect was my mirror, despite all the nice things that I had on the previous slide, all the check marks? You can ask the question, in what sense these two categories are these categories equivalent in any way? Not in good ways. You cannot, they're not equivalent as Brady tensor categories. Something goes wrong somewhere, and this has been a puzzle for a while, and historically it motivated us to not to resort to this quantum group immediately, because I must say that the way it originally appeared was a bit ad hoc. There was no regular procedure to derive that quantum group from conformal field theory. There was some ambiguity, and for that reason, every success, every check mark that I had on my previous slide was really viewed as kind of miracle, and we were excited at the time about it. But then it turned out that things stopped being extremely nice at a certain point, that tensor products behave differently on the two sides, in two categories. So we just wondered whether the mirror was a little bit too fancy, and we chose it, replaced it with a more simplistic mirror. And simplistic means this: the quantum group has E and F type generators, and it turns out that the screenings themselves, which you do see in conformal field theory, are in fact associated with only the F generators. So the E's in that quantum group were brought more or less by hand. You don't see them in conformal field theory, and the original motivation was that if you do without these, you might be able to get somewhat more precise correspondence between Hopf algebra side and the conformal field theory side. That's what actually was what brought Nichols algebras into the game. The notation here is as follows. You just take a complex plane, choose a direction, draw a number of parallel lines, and put vertex operators of your conformal field theory on these lines, and then you put as many screenings on the left and on the right as you want, as would fit, and you integrate. Integration is part of the definition of the screening. So as I said, there was a residue, but there is also a possibility to think of this residue as some integral. So you integrate. This picture means that there are two screenings which are identical, just integrated on the left up to the point, the position 0 of your vertex operator, and one is on the right. You can also do without the vertex operator insertions. You can just integrate screenings along your line, whatever this means, from minus infinity to plus infinity, because when these on the line, they can be transposed at the price of numerical factors. You can always assume that they ordered that the integration domain is such as shown here. So that possibility to transpose actually means that you have two braided vector spaces. X is a braided vector space whose basis is the different species of the screenings, and another vector space which is the different vertex operators sitting at 0. So it turns out that these constructions can be multiplied together. They form an algebra, and moreover, they form a Hopf algebra. To be precise, a braided Hopf algebra. And at a certain point, it turned out that this is the Nichols algebra read off directly from any conformal field theory, and I will try to explain how this is done. So, as I said, I want to turn the space of my linear space of my lines with crosses into a Hopf algebra. So, what do I do? Let me first tell you how what the coproduct is. The coproduct is just a pair of scissors, and I just cut this line into two, and therefore arrive at the tensor product. But I do it blindfolded, and I don't quite know where I apply my scissors. So I can do it such that to the right of the cut there are no crosses, or there is one cross, there are two, or all of them are on the right, which means that this is the map. And of course, scissors is not a very good notation, so now you know where tensor product notation comes from. It's just a simplified form of writing a pair of scissors. That's the way most people write this. And the product is also something very simple. When you want to take the product of this line with a single cross and the line with two crosses, you put every line, all the crosses on the same line, but you sum over the possible positions that the new cross can take among the old ones. So first it just gets attached to the left. That means nothing happens. Then it can move past the first one to this position, which means it's braided once. That's the braiding operation. Or it can actually go to the rightmost position, which means you braided through two original crosses, and that's how you multiply these things. And braided Hopf algebra, there is also an antipode, which is roughly the contour reversal. And braided Hopf algebra axioms are satisfied. And we reinvented Nichols algebras that way. The Nichols algebra is whatever is generated this way as algebra by single crosses, by multiplying lines with a single cross. There are two definitions, there are more, two equivalent definitions, both of which emphasize different parts of what Nichols algebras are, and both of which are very important. Given a braided vector space X, Nichols algebra B of X is a braided Hopf algebra such that is zero component is just nothing. The first grade is just X itself, and this X is exactly the space of all primitive elements. with respect to your coproduct, and it generates all of B of X's algebra. Equivalent definition is this. You just take the your tensor algebra of your vector space, and you take the quotient over a rather fancy kernel, the kernel of an operator which is braided symmetrizer or quantum symmetrizer. You do it this way. You take the sum over, okay, you do it grade by grade, of course. So in grade n, you take the kernel of this particular shuffle permutation, and it is defined this way. You take the sum over the symmetric group. Of course, these sigmas must be reduced of minimal length. Then you Matsumoto lift them to the braid group just by replacing your elements of your set theoretic section from symmetric group to the braid group, and you just made this thing, the braid group element, act on the tensor product of my braided vector space. So these definitions are equivalent, and to me today the second one will be very important. I think I will skip how I play with the crosses and things to construct modules, and I will define for you Nichols algebras, show to you how Nichols algebras are extracted from conformal field theory more formally. The good setting is, of course, that you take a finite-dimensional complex Lie algebra, take a number p, which will be very much p that I had before, no restrictions in the an case, for instance, on this p, and there are short screenings which are root rescaled by this number. There are long screenings such that the long and short screening directions are opposite. Screenings are oppositely directed, and the scalar product is -2. So this follows from comparing these two lines. Then the momentum tensor and the central charge are which commute with these both short and long screenings are easy to compute. And I will spend a while to discuss a theorem by Simon Lentner that makes sense, exact sense of that residue, or those a little bit loose integrals that I had on my previous slides. So you define the residue normally when everything is integer, all powers are integer. When powers are non-integer, like here, you take a small integral and you do integrate, and you substitute the limits, hence this difference. And when m is that special, you acquire m is generic. You acquire dependence on the radius of that small circle over which you integrate. So there is a variable which can very often be set equal to 1, but sometimes can be useful, and it's a little bit tempting, even though maybe not entirely justified, to have this notation for it. So the theorem by Lentner is that if you do that, the short screenings satisfy the Nichols algebra relations, and that's very general. I think that's an important statement. First of all, because Nichols algebras with diagonal braiding have been classified. That has also been a considerable achievement over last 10 years. I think that this happened already like about 10 years ago, and that classification can now be, with that classification at your disposal, you feel much more comfortable in the space of possible conformal field theories. And this applies in full generality. But of course, Nichols algebra is a quotient of that kernel, of that braided symmetrizer, and it can be very tricky. So how can you prove this for the screenings? Which Nichols algebra? Of course, this is the Nichols algebra corresponding to the braided vector space with this diagonal braiding. Let me just give you an example. Take rank 2, take this braiding matrix. So the Nichols algebra, which turns out to be arise as the quotient of the kernel of quantum symmetrizer, is can be described in terms of generators and relations. The presentation for it is this. You take T of x, F1 and F2 is the basis in your two-dimensional space X, and these are all the relations. So the commutator here is the braided commutator, that's the braiding matrix, read off from here, and the multiple commutators are just iterated commutators, exactly this way. So that's algebraic side. The conformal field theory side, you realize short screening in terms of your two fields, phi alpha and phi beta. You have long screenings, which are just minus p times longer. You look at the kernel of your long screenings, and you find the Razor algebra with that particular central charge. The central charge hints you that there should be a W3 generator, and there is indeed dimension 3 generator, which also sits in the kernel of the two screenings. The p is still that integer which is floating around. So this whole thing is a W algebra, which is Hamiltonian reduction of affine SL3. And then you do a lot more, because on top of this W3 algebra, you get a bigger W algebra, the truly logarithmic, so to say, W algebra. You get a particular field with particular conformal dimension, and from this you use your long screenings to produce the octuplet. So this is an octuplet algebra. There are just eight fields, and this is a higher rank 2 analog of the triplet model. The triplet model that I described in the beginning was just triplet, and this is what it is. Coming back to Lentner's theorem, how in this and in an infinite number of other cases you prove that exactly Nichols algebra relations are satisfied. I must say that here you may have wondered what this funny notation is, right? This is another. This is Cyrillic letter, and Simon Lentner has spent a year in Moscow, and it was a long time enough for him to pick up some Russian alphabet. So he insists that the screenings always be denoted by the Cyrillic Z. So it's not a 3, unfortunately. It's just another version of Z. So it's not. It's certainly. I didn't encourage him to do that, but things happen, right? With the definition of the residue that I gave you, you get rather complicated things as soon as your powers become non-integer, and you study the associativity much the way this is done in the standard theory vertex operator algebras, but you are more careful here, and you also face convergence problems. I will only briefly mention now. So what happens here when you rearrange application of two fields to a vector? So here the Y map is associated with letter W, and this Y map with the letter Z in the vertex operator algebra language. So this first thing is kind of keeping how different things talk to one another, and this is the degree of the power of Z of the corresponding variable. And here are the residues, particular residues defined that way. And what I have to study, that's the most interesting piece of this rearrangement, and I define this f minus. There is also an f plus, which I don't show to you, which is this. This derivative is, of course, a binomial coefficient. The point that generally a, b, and c here are non-integer, but summation here is over integers, positive integers. And when you have just arbitrary number of things falling on a vector from the left, you see that the analog of this f minus would depend on two types of variables. First, a string of mi, and then kind of lower or upper triangle part of the matrix. This is because this a, b, and c are associated with pairs of the vectors that you have here, a, b, and v. They are indeed, so you rename your a, b, and c into something like that, and in general you have a longer product, and these binomial coefficients that appear here. The claim is that I repeat my definition, I repeat the arguments, and then the claim is that this can be written as sum over symmetric group with what turns out to be exactly a quantum symmetrizer in front. So the one that I had, or braided symmetrizer. The necessary factors are accumulated here due to how you define this Q when sigma and sigma pi are from symmetric group and the product is reduced already, then you have multiplicativity. And an important thing about this f tilde is that this is a finite sum of Selberg type integrals. You can address the convergence problem. The claim of the theorem is that things can be put under control, and this formula totally makes sense. And it means that whenever, remember that the Nichols algebra was quotient by the kernel, so it means that whenever you have an expression in the Nichols algebra, the corresponding expression made out of screenings acting on any vector, you feed those particular parameters read off from this formula into the previous slide, and it turns out that whenever you have a relation in the Nichols algebra, you also have a relation, this same relation in terms of your screening operators. So it's quite difficult to say. I'll just come back to the previous slide for a moment. There is an expression for this, and its convergence can be studied, but it's not terribly illuminating. But the point is that it doesn't have to be. It only has to exist. You only have to check that. The whole trick here is that, miraculously or not, I don't think it's entirely trivial, you get this quantum symmetrization in front. So screenings do satisfy the Nichols algebra. Now, as I said, originally we ran across Nichols algebra trying to resolve, to improve the correspondence between conformal field theory and quantum groups. We believed that braided Hopf algebras read off directly from conformal field theory would do better job. Now Lentner has proved that they do absolutely what we had expected, but unfortunately they do not do more. So the first thing, of course, is that because these things are classified, is it the same? Is the wealth of Nichols algebras the same as the space, some reasonable space of good logarithmic conformal field theories? Well, not quite, because more data is needed. Given the Nichols algebras, you also have to specify a certain commutative co-commutative Hopf algebra and choose a category, and only then you can start working. The Nichols algebra itself is independent of this H, but everything else in your theory is dependent. That's not particularly bad, because that just means that Nichols algebra is an essential but not the only ingredient of, if you really attempt to do something like classification of logarithmic conformal field theories. So how representation categories, given everything you need, how representation categories are related? Again, they're not related as Braid-monoidal categories. Something deeper here is going on. As I said, trying to overcome this drawback in the correspondence with the original quantum groups was our motivation to go to the braided world, and we rediscovered Nichols algebras, but still they don't do the original motivation. Our original hopes didn't quite come true. It has been shown relatively recently what's behind the scenes, that you should use slightly different mirror, actually a curved or distorted or broken mirror, and things get better then. You should use not quite, if you want everything to behave nice under tensor product, you have to have a nasty tensor product on at least one side. You have to resort to quasi-Hopf algebras. That, as I said, coming back to the example of my triplet algebra and the quantum SL2, which is the simplest, these are not equivalent as Braid-monoidal categories, but this guy bears a quasi-Hopf algebra structure, a particular one with a particular, what they call it, associator, right? Three-core cycle living here. In case p equal 2, this quasi Hopf algebra structure was shown to be a Braid-monoidal equivalent to a category of symplectic fermions. Actually, this was done in 4 different ways. 4 is just because p is equal to 2. There will be more in the general case. And one of these 4 is conjecturally equivalent to, in all possible ways, to representation of the triplet algebra for my p equals 2. So it looks like I really distorted quite a lot of things, but the system turns out to be rather rigid in the sense that, persistent, in the sense that the SL2Z action on the center in this quasi setting is the same as we had before, the one which was so excited about being coincident on conformal field theory side and on the quantum group side. So maybe one day you would really do that looks a rather formidable task, to put together the ideas of Nichols algebras with quasi-Hopf setting. Well, not many people seem to be very willing to embark on that project. I think I have promised to skip a lot, right? So I will just mention that I'm done with the Nichols algebra story. Just mention another development that, given that duality, once again, in the example of my triplet algebra and quantum SL2, finite dimensional quantum SL2, or if you want, the rank 1 Nichols algebra could equivalently be placed, putting in place of that as we now know. So you can take this factor bigger, then this would become smaller, of course. You can take the Lustig divided power quantum group here, which is already infinite dimensional. So what this X is going to be, this is just a different, just to have you acquainted with a different view on the duality between Hopf algebra world and conformal field theory world. So as if, you can of course think of this as if some triplet structure, which has an underlying Lie algebra SL2, of course, it's been moved from the left-hand side, from the left left term to the right one. So this is Lustig quantum group, which also contains a Lie algebra SL2 inside. So this has become bigger, so this has to become smaller. You do play with the long and short screenings. and this is the horrible stuff that the full Lustig divided power algebra is when written out in full detail. I promise to skip that. I will just say that everything that you have studied so far agrees with this X being just Virasoro. So in my original setting, you had small quantum group and the triplet algebra. Here you have a non-rational theory because Virasoro, in this case, you no longer have a finitely many primary fields. You do have to deal with infinitely many primaries to begin with, but that's another reasonable setting for duality between Hopf algebra world and conformal field theory world. Yes. Some people go even farther. Some rather reckless, but, well, brave, I would say. People claim that theories which are not C2 cofinite are even better than C2 cofinite theories. And Terry Gannon, who's been around these days, is not exactly in this company, but is partly responsible for their behavior. So, for instance, they take, as the W algebra, they take the singlet, the middle part of the triplet algebra, and then it turns out that they have infinitely many simple modules, and not just infinitely many, continuously many. So the situation really becomes a bit special, but it turns out that you have continuous Verlinde formulas. That's pretty amazing that this whole thing comes out in a reasonable form at all. In finite-dimensional cases, we very often have Verlinde formulas which out of the S matrix coefficients produces for you finite-dimensional positive integer numbers. There, this index D becomes continuous. So you have to do a lot. You replace some with integrals, you choose a measure, and sometimes you even have to regularize. Amazingly, you do get integers quite often, and sometimes even positive integers. So that's pretty amazing. That, of course, shows that this whole thing, this idea is much deeper than just it goes beyond the finite dimensional context for sure. And these coefficients pass various consistency checks that you can imagine. So you may ask if that also has a counterpart on the Hopf algebra side. There are so-called unrolled quantum groups when you no longer have this K, but you recall that K is something Q to an H, and this makes things infinite dimensional, and you have an arbitrary eigenvalues for this H, and that's how you can get infinite continuous parameters into the quantum group settings. So conjecturally, well, I'm not sure how much this is correct, but at a certain point it was discussed that the singlet algebra is just has to do at least with unrolled version of my quantum group. I'm running off time, so I will just come to, I will entirely skip the lattices, and I will finish with saying that mirrors, various types of mirrors can do a lot of things for us. They can be very different, and we can be happy studying not exactly what's in front of our eyes, but what's behind there. Thank you very much.
Questions, comments? Well, no, if not, that's thank you.
Thank you very much.